Hi everyone and welcome back to Line. Today I want to share with you a new set of videos about applied machine learning for 3D vision. As you can see the screen, we can see several types of data. We have images, signals, 3D point cloud, meshes, and in this series we are going to see together how to manipulate them and the most important, how to build a model of machine learning or deep learning, how to train it and predict some things like classification, segmentation, completion part, all the things. So let's get started with the machine learning for 3D vision presentation, introduction. So let's understand just briefly the difference between machine learning, deep learning, and generative AI. So in the machine learning, we can use algorithms such as decision tree, which is based on entropy and information gain, for example, or random forest, or also XGBoost. This kind of algorithms are using, in fact, statistics and metrics like entropy to measure the disorder between data, how predictable is the data, and then to choose, for example, the first node. The deep learning, the main difference between machine learning and deep learning is like in the machine learning, we need to extract the features manually and then to get to provide to the algorithm the features, and then the algorithm will be trained on these features in order to predict the new things. The deep learning, we can provide to the deep learning model all the gross data, meaning if we are working with images or with signal, we can just provide the signals or images to the deep learning model. The second main feature of deep learning is like it's a neural network, which is based on several hidden layers. When we talk about hidden layers and depth hidden layers, meaning several ones. So we talked about deep learning. Generative AI is the fact of using, for example, for images autoencoder, for example, variational autoencoder, which is an encoder which the main goal of this autoencoder is to reconstruct the first image, and with this reconstructing, it's working like that. We have an image, we want to reconstruct it, and so we need to first to get an embedding of this image using the encoder and using the decoder to make to get the reconstruction from this embedding. This allows us, for example, to use this embedding and to add a noise on this embedding, to add like a translation, and then to get a generative image, another image. The LLM is working also with generative AI because, for example, ChatGPT or other model is to predict the next token using the probability of occurrence of the next one. So let's go ahead. So now we have several types of learning. Let's be focused on the supervised learning and unsupervised learning. When the supervised learning, meaning we have the labels, so we can do classification, segmentation, and regression, and so on. And in unsupervised learning, our goal is to get the correlation between data to form clustering and also dimensionality reduction as well. So this is an example. My examples, I love Harry Potter. And so in this example, you can see, let's say, a classification between characters of Harry Potter. If I want to make classification of images, let's say I have several images from Ron Weasley and Hermione Granger and Harry Potter and Ginny Weasley. So I need several images of them, and I need for the feature selection, let's say I want to use machine learning concept and not to provide just the images to the deep learning. So I need to extract features. So the question is, what will be the best features to extract in order to let the machine learning model learn well on my data. So one is to get feature which is maximizing the difference interclasses, meaning I want a feature which is very different between class and another. For example, the mark that we have for Harry Potter is only in Harry Potter, and we don't have this same mark on the other ones. So then we can say this feature can be interesting. Okay. Then what other feature can also be interesting? So we also need to minimize the difference intra-class. What does it mean? Meaning in the same class, we don't want to have a difference. We want to have this feature very consistent, very robust in the same class. For example, if you say, okay, the color of hairs, so maybe it will not be the best feature we can have. Why? Because it completely depends on the light. Okay, if we have a picture with a a high light, so maybe we will see the color of hair in the certain color, and if the photo is in dark, for example, so then the color of the hair will be different. So maybe this, then when we have the feature selection, we can provide them to the model, and then with the labels we can choose the machine learning model to train, and then train it and then get predicted. For the signals, for example, so you know that the square signals is in fact a sum of infinite cosinus and sinus, and we can images, and when we work with deep learning, we can provide the temporal signals, or we can also convert that using FFT, fast Fourier transform, and then to get the frequencies, and then to provide the frequencies to the deep learning. The main thing to understand is that the deep learning will act as we can see in this picture, meaning to trying extracting patterns in the signal. So the patterns the deep learning will be extracting can be in fact some kind of simple function like cosinus and sinus, but because the deep learning will extract several patterns, then the decision will be intelligent. So now let's go ahead with an image. So in fact, an image is like an array, okay, in 2 dimensions, and we have also in this array three channels, red, green, and blue. And for each channel, we have a value. Okay, we have rate, we have a value, and this value provide in fact the composition of this image. We can also convert the image from RGB, from red, green, blue, to gray, and we just need to apply a certain factor to each channel, to blue, to red, and to green, and then to sum all of them using the factor, and then we get the grayscale image. So this is data, 3D data representation. As we can see on the left side, we have the RGB depth, we have the voxel, the volumetric data, and the multi-view. If you don't know about that, you can see my series about the 3D computer vision. The beginning explained all of them. And then the right side, we can see the non-Euclidean data with the point cloud and the mesh. So this is kind of features very important from the PointNet model for the point cloud. So as you have in the first left corner, we can see irregular, unordered permutation invariance. What does it mean? The point cloud, different than images, that image is structured, in fact, in like of a table. And if we invert, for example, the point from the images, so then it will be different. The image will be different. But at point cloud, you can also unorder the point. It will not affect the point cloud, so you can make them different, and that's why it's completely unstructured also data, unordered data. We have the robustness to rigid transformation. This is again the PointNet, because we have in the model PointNet an operator which called TNet, as we can see also in the video of 3D computer vision, and this operator allow us to get translation and rotation to be invariant of rotation and translation. So this is the normals. So you can see the normals of point cloud. So we have the points, and the normals are completely to outside, and this provide, in fact, for example, for the mesh, it's provide the effect of meshes to be rigid. And so what is a mesh? A mesh is in fact a triangle, several triangles, when each triangle is in fact composed by 3 vertices. Each vertex is in fact V1, V1x, V1y, V1z for it's 1 point, for example. So we have 3 points for a triangle, and then we have one normal, and we can see here the coordinate of the normal, Ni, Nj, and Nk for the coordinate of the normal. So now we see that. Okay, let's started now with the code and in debug mode. So let's first create an image. As we can see, a random image with height and width. This is a completely NumPy image, just to show that an image is in fact just an array, and when you can just plot it. So we have a random red. This means that it will provide random numbers in this shape. So the shape will be 100, 100, and 3 for the 3 channel RGB. Okay, so then we can insert in this image. What can be different and what can be interesting is to insert, in fact, a part of this image in another image. So a black image, in fact, is just an np.zeros, okay, to get the all the image to get it in black. So we can just have 0 for R, G, and B, and the result will be in black. And then we can insert in this black image, so you can see it outer height and outer width for 300 and 303 for channels, and this will be a black image. And then to combine the black image with the first one of random, and then this will create, in fact, a black image, and inside, in the middle, we will see, in fact, our random image with several colors. Let's go ahead, create random image, so just so that, and then start Y and start X just to get the middle, okay? And then we just insert using indexation. So you say, okay, between 100 and 200, okay, let's see. Start Y, so you can see start Y here, yeah, between 100 and 100 plus inner height, which is 100, so meaning between 100 and 200, and between 100 here and also 200 here, just insert the random image, and then we can get, in fact, the final result of the image. Let's now just see for the fun the picture and just to explain that. And so now what we did together is to create the random RGB image, then to create a black image using zeros, and then to insert the RGB image inside this one in the 100 and 100 here. Here, if you don't know how to generate it, it just randomly generate for a 3D point cloud, meaning in the three component team, okay, components. And for the signals, in fact, is just a sine signal. Just this one can be also important for you to understand. Create now the signal, so you're just using np.linspace in order vector for x, and then the function is, in fact, a sine wave, and we just add to the sine wave a noise when the noise is provided by the noise level times the random for the same number of ones. So then we have the signals, and this is providing, in fact, the noise in the signals. So that's it for now. In the next video, we are going to see together how to extract features from 3D point cloud and starting working with great model of machine learning and deep learning. Thank you for listening to me. Share this video and continue. Go ahead with new technology.